Hello and welcome to the Hornet's Nest. I'm the operator, and here we do a lot of learning, a lot of reading, a lot of labbing, a lot of mistakes, a lot of making mistakes, a lot of lessons learned. Appreciate you all for joining in. Currently, what I'm doing right now is learning a lot about high performance compute. And I'm learning about the architecture, how it's designed, learning about provisioning, obviously with Warewulf. Here you can see here up on the page, the previous live streams, I've gone through the introduction to the design architecture and overview of Beowulf, which is the origins of HPC, and then we read through here, and even went through a lot of the documentation here. But what I have begun to do is really map out what's needed to get started within HPC. And I did that in Procreate on my iPad, and I've just going through a lot of notes at work and really trying to connect the dots of how does HPC work. So I don't have that in Excalidraw, but I do have that on my iPad. And let me go to Procreate real quick. Let's see. So anyways, this is my home network that I've got going on with my personal PC, or my mini PC actually, which is my B-Link SER9. And then I've got my virtual machines within that, and my virtual bridge 0, virtual bridge 1, my worker nodes, Almabrain, which is connected to my GitHub repo, and my management server. Now, this is where we are now making progress. So let's go ahead and focus. Thank you. We are up to 14 subscribers now. That's pretty awesome. Anyways, so we are paying attention to the management server, management 01. Well, why are we paying attention to management 01 so much? Because management 01 is hosting our Warewulf daemon, and WWCTL is how we control everything. So that's why this is relevant. All right, so the default profile within there, I have NFS mounts configured. I have additional profiles created that have images put within those profiles, and I can push those profiles to any one of my worker nodes. Now, the profiles are baked images. If I want to add anything to a specific server, I'd have to do that with an overlay. I could do that to a server or a cluster of servers. All right, now let's see. I'm gonna pull up Visual Studio Code. We'll take a look at that for a second while I pull up this NIST information. All right, so I can connect to the management node using SSH admin at 192.168.1.19, and I'll do host name CTL, and we can see this is Rocky Linux 10.2. So I've gone through the Warewulf documentation. We have Warewulf currently running. In the previous lives, you've seen me get those images up and running. The next thing is really kind of understanding storage. But I made a lot of progress with talking out with others and my understanding of the architecture of HPC, but I don't like the way that this is drawn. Not to take away from anyone who did it before, but I don't think like this. So it's a very, like, I had to ask a lot of questions to understand it, and it's cool that I understand it. And even though I understand it, I still look at it like with my head tilted to the left. So that's kind of what I'm gonna do, is let's do Control S. I'm gonna take this. I'm gonna copy that. Let's go to Excalidraw. And we're gonna do a new one. Let's go Homelab. And this will be renamed HPC architecture. Actually, let's just do cancel. And here, Control V, put that there. Can make that a little bit smaller. Cool. All right, and then I know that might be weird. Okay, there. For whatever reason, it just makes more sense this way. So I'm gonna recreate this real quick, and then I will be ready to move on to the point where I've got my provisioning server done. I'm going to do storage connection and the scheduler, which will be Slurm. All right, and it's 10:49. Not bad. Okay. So let's start off. That's a horrible cloud. What is going on? This was the problem that I had the other day that I did not like about this application. Like, why is everything faded? Oh, I took opacity down. That's my fault. Oh my God. Yep. I'm never going to do this again. All right. So Excalidraw really sucks. In other words, I'm going to move on to reading and I will show you all. This kind of looks all right, but this still also kind of sucks. And let's go to docs. All right. Anyways, jeez, I hate that. That was a waste of time. Okay, so high performance computing security. Abstract security is an essential component of high performance computing. HPC security systems often differ based on the evolution of their system designs, the applications they run, and the missions they support. An HPC system may also have its own unique security requirements, follow different security guidance, and require tailored security solutions. Their complexity and uniqueness impede the sharing of security solutions and knowledge. This special publication aims to standardize and facilitate the information and knowledge sharing of HPC security using an HPC system, reference architecture, and key components as the basis of an HPC system lexicon. The publication also analyzes HPC threats, considers current HPC security postures and challenges, and makes best practice recommendations. Posture threat analysis. Okay. All right, so let's see. I'm reading this on my iPad too. It's just so much easier to read this stuff in Notability. So I'll pull back up my internet browser so you all can see this. Sorry about that. Blink out, a little technical difficulty. We're back. So just went through the keywords. ITLs, Information Technology Laboratory, the National Institute of Standards. So, table of contents. Main components of high performance computing zone, components of the data storage zone, parallel file system, archival, and campaign zone, storage, burst buffer, components of the access zone, components of the management zone, general architecture and characteristics, basic services, configuration and management, HPC scheduler, and workflow management, HPC software, user software, site provided software and vendor software, containerized software, and HPC. HPC threat analysis, key HPC security characteristics and use requirements, threats to HPC function zones, access zone threats, management zone threats, high performance computing zone threats, data storage zone threats, other threats. A lot of threats. Okay, and then we got HPC posture challenges and recommendations, access control via network segmentation, compute node sanitation, data integrity section, securing containers, achieving security while maintaining HPC performance. That sounds like sounds like a good section to pay attention to. All right, challenges to HPC security tools, conclusions, and all right, not bad. We can get through this tonight. So we're on introduction. Sorry, just if you zoom in just a little bit. Let's take that zoom out. I don't know why this zoom is so much. this is annoying. Oh boy. There we go. Control Shift minus. Yeah, Jesus. Alright. Alright. All right, made my notes. Now I'm on the introduction portion of this. All right, 2015 Executive Order 1307. 13702 established the National Strategic Computing Initiative to maximize the benefits of high-performance computing for economic competitiveness and scientific discovery. The ability to process large volumes of data and perform complex calculations at high speeds is a key part of the nation's vision for maintaining its global competitive edge. Well, that just got serious very quick. Executive Order 13702. Executive Order 131702. Administration of Barack Obama 2015 Executive Order 13702, creating a national strategic computing initiative. July 29, 2015, by the authority vested in me as president by the Constitution and the laws of the United States of America, and to maximize the benefits of high-performance computing, HPC research, development, and deployment, it is hereby ordered as follows. Section 1. Policy. In order to maximize the benefits of HPC for economic, competitive, and scientific discovery, the United States government must create a coordinated federal strategic and HPC research strategy and HPC research, development, and deployment. Investment in HPC has contributed substantially to national economic prosperity and rapidly accelerated scientific discovery. Creating and deploying technology at the leading edge is vital to advancing my administration's priorities, spurring innovation. Accordingly, this order establishes the National Strategic Computing Initiative, NSCI. The NSCI is a whole of government effort designed to create a cohesive multi-agency strategic vision and federal investment strategic executed, or, oh man, I butchered that sentence. The NSCI is a whole of government effort designed to create a cohesive multi-agency strategic vision and federal investment strategy executed in collaboration with industry and academia to maximize the benefits of HPC for the United States. Boy, I had to slow down. All right, and then I thought that was interesting because Warewulf comes from NASA. So, yeah, it's interesting how we get our advancements, right? So moving on, let's see. I am back to the NIST documentation. Where is that at? No, that's in my notes. All right. Weave. All right. That's just okay. The ability to process large volumes of data and perform calculations is a part of the nation's vision for maintaining its global competitive edge. Security is essential to achieving the anticipated benefits of HPC. HPC systems bear some resemblance to enterprise IT computing, which allows for the effective application of traditional IT security solutions. However, they also have significant differences. An HPC system is designed to maximize performance, so its architecture, hardware components, software stacks, and working environment are very different from enterprise IT. Additionally, most HPC systems serve multiple projects and user communities, leading to more complex security concerns than those encountered in enterprise systems. As such, security solutions must be tailored to the HPC systems requirements. Furthermore, HPC systems are often different from one another due to the evolution of their system designs, the applications they run, and the missions they support. An HPC system frequently has its own unique method of applying security requirements and may follow different security guidance, which can impede the sharing of security solutions and knowledge. A zone-based HPC reference architecture captures the most common features across the majority of HPC systems and segues into HPC system threat analysis. Key HPC security characteristics and use requirements are laid out alongside the major threats faced by the system and individual function zones. This publication is intended to be a conceptual guide, not a checklist of requirements. All right. An HPC system is divided into 4 function zones. The high-performance computing zone consists of a pool of compute nodes connected by one or more high-speed networks. The high-performance computing zone provides key services specifically designed to run parallel jobs at scale. The data storage zone comprises one or multiple high-speed parallel file systems that provide data storage service for user data. The high-speed parallel file system are all designed to store very large data sets and provide fast access to data for reading and writing. The access zone has one or more nodes that are connected to external networks, such as the broader organizational network or the internet. This zone provides the means for authenticating and authorizing the access and connections of users and administrators. The access zone provides various services, including interactive shells, web-based portals, data transfer, data visualization, and others. And then you have the management zone. Interesting. I see how they kind of started from internal and then built their way out. So anyways, the management zone comprises multiple management nodes and/or cloud services clusters through which HPC management services are provided. The management zone allows HPC system administrators to configure and manage the HPC system, including the configuration of compute nodes, storage networks, provisioning, identity management, auditing, system monitoring, and vulnerability assessment, various management software modules, job schedulers, workflow management, and the domain name system DNS run in the management zone. All right, so here is the zones. We got access zone, data transfer zone, web portal, high performance computing zone, compute zone, storage node, scheduler, resource manager, front end provisioning server. In the management zone, data storage. Yeah, it's at this point I've been staring at it for so long. It's pretty self-explanatory now. Oh man, there's a concurrent viewer. Oh wow. Hello. Thanks for watching. Anyways, so then we've got main components of high performance computing. An HPC cluster consists of a collection of independent computing systems called compute nodes, which are interconnected via high-speed networks. Compute nodes have the same components as laptop, desktop, or server, including central processing units, memory, disk space, and network interface cards. However, they are architecturally tuned for the requirements of HPC workloads. That I didn't know. All right, what page is that? That's two. Compute nodes have the same components ever. All right, it's HPC architecture is a compute node may not have local disk and instead use the data storage services of remote storage servers. A compute node may not have local disk and instead use the data storage services of remote storage. Okay, NFS. In addition, there may be different types of nodes for different types of tasks. And some compute nodes are equipped with hardware accelerators to speed up specific applications. For instance, compute nodes often utilize graphics processing user GPUs to accelerate modeling and simulation, or AI machine learning model training. Gotcha. In addition, there may be different types of nodes for different types of tasks. Some compute nodes are equipped. Go. Okay. An HPC compute node has its own software stack installed. The OS compilers, software libraries to support applications. The installation and configuration of the software stacks are cluster-wide, centrally managed, and controlled by the management zone. The number of compute nodes in an HPC system ranges from a few nodes to hundreds and even tens of thousands. Okay, so there's some things that I learned today, which just is like, runtime commands and the cycle of what it takes to send out a command to thousands of different servers at one time. Beauty of change management. All right, a frequent requirement of HPC networking, which interconnects computer nodes and file systems. It is to have high throughput and low latency so that the compute nodes and parallel file systems, PFS, in the data storage zone can work as one supercomputer. The exact requirements for bandwidth and latency are dictated by the intended workload. HPC networking often employs specifically designed protocols, networking cards, processor nodes, and switches to optimize networking performance. The popular HPC interconnect networking includes InfiniBand, Omni-Path, Slingshot, so familiar, Ethernet, and others. Well, I got Ethernet at home, but I'm not familiar with Omni-Path, so that's new. A high-performance computing zone typically utilizes non-high-performance communication networks like Ethernet as cluster internal. Oh yeah, gotcha. Networks that connect the high-performance computing zone with the management zone and access zone for traffic associated with maintenance and activities as opposed to HPC traffic. So this is important. It's cluster internal networks that connect the high performance so let's go highlight Ethernet. Man, what's going on? Oh, Control Z. So Ethernet is down. There you go. Dude, I don't know what is going on sometimes with this computer. Ethernet. So Ethernet. A high-performance computing zone typically utilizes Ethernet as cluster internal networks that connects the high performance computing zone with the management zone and access zone for traffic across associated with maintenance activities. And that would be this section here. So the management zone and the access zone are using the Ethernet connection. Probably I'm not going to specify the speed. That's here. They're using this connection to access and talk to the compute, but the compute and the storage are using this high speed to talk parallel to each other as one machine. All right, so then we go back down. We're on, what time is it? 11:24. All right. Okay, so then several different classes of storage systems may be present inside of the data storage zone. General storage systems within this zone cannot be effectively separated from the HPC resources that they support. From an administrative privilege perspective, typical classes of storage found within this zone include parallel file systems and archival file systems that support campaign storage. And protect against data loss. HPC systems may have other file systems that store non-user data. For instance, the management zone often has its own file system that stores the OS images and configuration files. In that case, so storage, for instance, the management zone often has its own file system that stores the OS images and configuration files. Yes, that makes sense. In that case, the file system is included in the corresponding function zone. HPC applications' initial data, intermediate results, and results are stored in the data storage zone and can be accessed during the application runtime and after the application's completion. External HPC users can also access user data through the login nodes and/or data transfer nodes in the access zone. The storage capacity of these file systems is often measured in petabytes and can reach up to exabytes. The file systems, not in my lab environment, my home lab environment, that is. File systems within the data storage zone will generally use a transport mechanism appropriate to the tier. For example, high bandwidth file systems may be attached to the HPC resources high performance network, while lower bandwidth file systems may use 10 gigabytes or 100 gigabytes Ethernet. Access control for high performance compute file systems is enforced by the operating system software of nodes on which these file systems are mounted. As such, file systems should not be mounted outside of their security boundaries. That makes a lot of sense. A rogue system that can mount a file system will have complete control of all file system data and can spoof packets on the high-speed network and can possibly gain privileges elsewhere within other zones of the HPC security enclave. Parallel file system. Since HPC workloads can vary significantly, a parallel file system is often required to support read-intensive and write-intensive applications with sequential and random access patterns at speeds of up to terabytes per second. Wow. Commonly seen file systems include Lustre, GPFS, and IBM Spectrum Scale. During procurement, a PFS will typically be designed to hit a particular aggregate bandwidth target rather than a capacity requirement. These parallel file systems will typically consist of a cluster of systems to maintain metadata about files and locations, as well as servers that act as storage targets. Clients that mount the file system will typically load the file system client software via kernel module. Servers will have backing storage arrays configured with dozens of disks and redundant array and an inexpensive disk RAID strategy. Both GPFS and Lustre-based parallel file systems are prone to performance degradation when a certain capacity threshold is reached. Wrecked. These file systems may be regularly pruned or unwanted files with a strategy that's important. This is government documentation NIST. I'm putting you guys down. Sorry. It's prone to performance degradation. When a certain capacity threshold is reached, these file systems may be regularly pruned or unwanted files with a strategy decided by the file system administrators. Some deployments will delete files older than a certain age, which forces HPC users to transfer job output to a longer-term file system, such as a campaign storage. Parallel file systems tend to be somewhat unreliable, depending on the types of activities being performed by running jobs and users. Because these are distributed file system software must solve distributed locking of files to ensure deterministic file updates when multiple clients are writing to the same file at once. Additionally, parallel file systems are susceptible to denial of service conditions even during legitimate user operations, such as listing a directory with millions of files or applications that perform file locking semantics. Sometimes I hate this thing. It does not do what I want it to do. We're right about at an hour. I'm going to take me a little 5 minute, and we're not halfway through this, but we're getting through this. I'll be up a little late tonight, so we're gonna take a little break, and then I'll be right back. Let's see, what's the timer set to? Oh my gosh, 2 minutes? No. Break time. 10 minutes. Give me 10 minutes to rest my eyes or do something different. I'm staring at these screens. I gotta stand up. Boy, oh boy, oh boy. Break. There we go. Sorry. Okay. I will be right back in 10 minutes. You all enjoy the music. All right. Yep. So we're currently sitting at 14 subscribers, and we're gonna get back to our reading. I didn't feel like reading for the whole 10 minutes. Sitting back here, so I need to get to bed here soon. So let's keep on going. So the term campaign is understood here as a collection of coordinated projects that are working toward a common set of goals and deliverables. Archival and campaign storage systems represent a class of storage that is more resilient to failure conditions than a parallel file system and is often less expensive per gigabyte. These advantages come at the cost of bandwidth and an increased latency of data transfer. While a parallel file system acts as a temporary short-term scratch file, increased latency of data transfer. While a parallel file system acts as a temporary short-term scratch file system, campaign storage supports the long-term storage needs of a project over its life cycle. Finished data products that support scientific publications or other high-value data sets may also be stored in an archival file system. The retention time for data on a campaign storage file system is measured in years, while the retention of the data within an archival storage system is measured in decades. Both campaign and archival storage systems might employ low latency disks, such as solid state drivers or non-volatile memory express and NVMe drives within a small tier or storage that acts as a cache and are backed by cheaper, higher capacity media, such as spinning disk and or tape media. Burst buffer. Burst buffer commonly refers to a caching mechanism for storage systems. For applications that require extremely low latency or high bandwidth memory to disk data transfer during runtime, intermediate storage layers, Burst buffer commonly refers to a caching mechanism for storage systems. For applications that require extremely low latency or high bandwidth memory to disk data transfer during runtime, intermediate storage layers that contain burst buffers have been incorporated as brokers to primarily mitigate the effects of input-output contention and the bandwidth burden on parallel file systems. These burst buffers can prefetch data from the parallel file systems before a computing job begins and stage data out to a parallel file system after a computing job has completed. This saves job runtime that would normally be spent performing bulk input-output to parallel file systems and allows it to be spent on computation instead of typical high-performance infrastructures. Okay. Typical high-performance infrastructures contain the following intermediate storage architectures. No local burst buffer architectures. This burst buffer is co-located with a corresponding HPC compute node. This is advantageous for its scalability and improves the checkpoint bandwidth because the aggregate bandwidth increases in proportion to the number of compute nodes. Remote share burst buffer architectures. Burst buffers are shared between multiple HPC compute nodes that are hosted on an input-output node. This is advantageous for facilitating the development, deployment, and maintenance of these architectures. There are also HPCs that can contain mixed burst buffer intermediate storage architectures, which combine the strengths of node local and remote shared burst architectures. Okay, let's not play hero today. Page was burst. Cool. We're going to use the power of AI. This section makes 0 sense to me. Burst buffers are a caching layer sitting between compute nodes and the parallel file systems. The shared storage backing in HPC. Yep. The problem they solve: compute nodes generate / consume data way faster than the parallel file systems can read write, especially for checkpointing. Periodically dumping job state so you can recover from a crash or a bursty input-output without a buffer. The job stalls waiting on disk. So a burst buffer, usually fast flash and VM storage, sits in between. Before job starts, it prefetches data from the parallel file system. While the job runs, it absorbs fast writes at memory-like speed. After the job ends, it stages the data back out of the parallel file system in the background. The compute node never waits on the slow parallel file system directly. It hands data to the burst buffer and moves on. Interesting. Now, the question becomes, does that get used for campaign file systems? Have been incorporated as brokers to primarily mitigate the effects of input-output contention and the bandwidth burden on parallel file systems. Let's go ahead and lock in. We can get back into our focus. We know we're at 14 subscribers. Here we go. These burst buffers can prefetch data before a computing job begins and stage data out to a parallel file system after a computing job is completed. This saves the job runtime that would normally be spent performing bulk input-output to parallel file system, allows it to be spent. It's pretty cool. Each burst buffer is co-located with a corresponding HPC compute node. This is advantageous for scalability and improves the checkpoint bandwidth, because the aggregate bandwidth increases in proportion to the number of compute nodes. Remote shared burst buffer architectures. Burst buffers are shared between multiple HPC compute nodes that are hosted on an input-output node. This is advantageous for facilitating the development, deployment, and maintenance of these architectures. There are also HPCs that can contain mixed burst buffer intermediate storage architectures, which combine the strengths of a local node and remote shared burst buffer architectures. Components of the access zone. A typical HPC system provides one or more nodes through which users and administrators access the system. At least one of these nodes is a login node where users have access to shells to launch interactive or batch jobs. Interactive or batch jobs. The batch jobs, schedule it out, runs everything. Interactive, you can do a little bit more. Some of these login nodes may also have specialized visualization hardware and software with which users can conduct interactive and or post-execution visualization of their data sets. There may also be one or more data transfer nodes that provide services to transfer data into and out of the HPC system, and may even provide storage mounting services like network file systems, common internet file systems, and server message block SMB, and file and user space fuse, and based SSH file system SSHFS. The security, wow, that was a lot of different file systems. The security posture for data transfer nodes often uses this architecture of Science DMZ instead of a pass-through firewall device because of the performance impact firewalls may impose. Many HPC systems now provide web portals via web portal nodes that enable a variety of web services to HPC system services. So this would be the data transfer nodes. This makes sense. Sending storage into the cluster. And the most likely, probably common one would be NFS. I know that's what I'm using right now. But my management node is my storage node right now. All right, many HPC systems now provide web portals via web portal nodes that enable a variety of interfaces to HPC system services. Components of management zone. The complexity of HPC systems requires a significant infrastructure to operate and manage it, which is collectively referred to as the management zone. The management zone may consist of servers and network switches that enable various functions for operating the system with efficiency, effectiveness, and stability. One important characteristic of the management zone is that it has a separate security posture because non-privileged users do not need to access the management servers or services in a direct way. Privileged users responsible for configuring, maintaining, and operating the HPC system access the management zone servers and switches through extra security controls. For example, from the public-facing login nodes, they may go through a bastion host that is typically located in the management zone, or they may establish a virtual private network with separate authentication and authorization or other appropriate security controls to breach the management zone. All systems are configured on networks that are not routed beyond the perimeter of the HPC system so that only nodes like compute nodes and storage nodes can access services. Okay, the services provided by the management zone have clearly defined protocols and can be implemented as running on assigned hardware platforms or run virtual machines on a dedicated set of hardware resources. The fact that the management zone has a clear and separate security posture helps with risk assessment and the selection of controls to secure the management zone and management. All right, we're gonna pick up on this tomorrow. Page 7, and I think, what is it, 13 pages? Oh no, there's 35 pages. Yeah, we were not finishing this tonight. Anyways, we left off on basic services. All right, see you all tomorrow. Bye.